for integral of dx over 2 times x minus 5 over 2, parentheses squared, minus 1. So this thing in the square parentheses should be my u. U is actually equal to 2x minus 5. See, because this you could rewrite this as 2x minus 5 quantity squared. I multiply the 2 through, I get 2x minus 5, you know. Anyway, the point is du is 2 dx, so dx is 1/2 du. And try to finish this thing here. 1/2 du over u squared minus 1. So I bring the half outside, it leaves me with a 2. I get a minus inverse hyperbolic tangent of u plus a constant, which is minus 2 inverse hyperbolic tangent of 2x minus 5 plus a constant. I wanted to show you could do it the same way as we did the other two if you know about the hyperbolic functions. That said, this is like not the best way to do this problem. The best way to do this problem we actually learned in calculus 2. All right, there's something called the partial fractions decomposition, which is the natural weapon to wield against this integral. All right, so I will not test on example 12 because I feel like it's actually a calc 2 problem, which I've solved in a wrong way. But I think it was useful because it is again illustrating the same ideas. Now this problem might be on the test. This is within our scope, the inverse tangent ones. That would be like a bonus question. It's a little bit off over the edge. All right. Now there's something that has been sadly missing from my the vast collection of u-substitution examples I've shown you. And the thing that has been missing, which is unfortunate for us, because you really do need to know how to do this, is bounds. Right? We have to sometimes deal with integrals that have bounds, definite integrals. And the way we do u-substitution for definite integrals, it involves an extra step, right? Involves an extra step. And the extra step is changing the bounds. So before I get into that, did you have any questions about homework? Because you came in, I asked if there were questions about homework after before you came in. Oh, I did the question? Oh, okay, good. Woohoo, my good fortune. All right, so let's see here. Suppose we had something like integral let's talk about examples. U-substitution with bounds. So what's Wednesday? Wednesday's our day of review for the test, right? Is that right? Yes. Wednesday's a test review. Friday we're not meeting. Monday's a test. That's right. So any kind of, as you look back over the last few weeks, if there's a problem that's in the homework, but I just
8 through 10, right? 8 through 11, sorry.
Yeah, I'm not.
11, sorry.
Yeah. Right. I mean, honestly, I do think it actually would be very healthy to go back and look at everything. Everything past the point of limits really is helpful for you from going on because, I mean, there's a part of the final which is on limits, right? That's just part of calculus 1 is the study of limits and, calculating derivatives from the limits. That's something we spent time on. That's something, I will test on in the final. But I would be dishonest with you if I didn't admit that there is a phase change in here, right? Once we get past the point of limits, we start calculating things, right? We develop this, set of algebraic principles that we apply, right? We don't actually do, when's the last time we actually calculated a limit in here? Right, it's been a minute. Okay, fine, we did some for the area problem, but those are even different kinds of limits. That's really, we just gave them the same name. That's kind of like, well, anyway.
Since you talked about the final results.
But I do think that reviewing the differentiation homework in principle could be helpful, because differentiation is like, you must be solid on differentiation to do anti-differentiation well, right? That's how we check our answers. Your question?
It's concerning the final. The final will be one test,
The final is based on test 1, test 2, and test 3, but it's not exactly the same problems. So
So we should study those tests.
that would be a good starting point, yeah.
We haven't studied them for them.
I have written solutions for the 3 tests, so that's kind of the study guide, yeah. The course is a study guide for the final. What a friend of mine used to always say. But no, I don't. Let's see here. So example of u-substitution with bounds. How about this? If we have integral from 0 to, let's say, pi squared of x sine of x squared dx. So this is a integral, a definite integral, right? And so as you face definite integrals that involve u-substitution, you really have 2 choices. Let me show you both ways. I'll show you both ways. All right, first of all, I'll do it the way that's kind of, I don't know, when we say that, neither way is better than the other, really. U equals x squared. So du is 2x dx, right? So x dx is really 1/2 du. So this gives me sine of u times du over 2, right? Now that's the first half of it, but when we have bounds, we have an integral of bounds, we have 3 things we have to change. We have to change the integrand, we have to change the measure, which is the du part, the dx part, and we also have to change the bounds. So x equals to pi squared, right, implies u equals to what? If x is pi squared, u is what? Pi squared squared, right? Pi to the 4th. And if x equals to 0, u equal to 0. So I change the bounds. 0, pi to the 4th. Then this has antiderivative minus 1/2 cosine of u. FTC2 says evaluate from 0 to pi to the 4th. Answer, minus 1/2 cosine of pi to the 4th plus 1/2. Final write out, minus 1/2 of, good grief, minus a minus 1/2 cosine of 0. So minus minus gives me a plus. I've got 1/2 of 1 minus cosine of pi to the 4th. So that's one way. You can change the bounds. The other way to do these kinds of problems is a 2-step. brother. That reminds me, I need to fix his ringtone. So the other way to do this is two steps. And the two steps are to first find the antiderivative using u-substitution and then apply the FTC. So here's the other way of doing it. Example 13 tilde. We do integral of x sine of x squared dx. You go, oh, okay, well, this is integral of sine of u times du over 2 if I make a u equals x squared. So du is 2x dx. X dx is 1/2 du. Substitution. So this is kind of everything I just wrote over there, right? So that's minus 1/2 cosine of u plus a constant, which is minus 1/2 cosine of x squared plus a constant. So I find the antiderivative for the problem in x, and I say thus, by FTC2, the integral from 0 to pi squared of x sine of x squared dx is minus 1/2 cosine of x squared evaluated from 0 to pi squared. Now, some folks, when they do a problem like this, they will even write pi squared equals to x and 0 equal to x to emphasize what's going on, and then you plug it in. That's 1/2, right? So we're back to, of course, 1/2 of 1 minus cosine of pi to the 4th. So, I mean, it's math. It's not like you're going to ask what the problem means to, one society and get one answer, ask what the problem means to a different society and get a different answer. I mean, it's math. There is a true answer. There's no gray here in that sense. So what's the difference between example 13 and example 13 tilde? The example difference is I changed the bounds, right? What you cannot do is make a u substitution where you just change the u's and leave 0 and pi squared here and just pretend that makes sense, because it does not. And it will get you into trouble. Maybe not the first time you do it, but at some point you'll get your thought process interrupted as you're writing things down and be led. If you write things which are untrue, you'll be led to make untrue steps. It's just the nature of math. So, a question? No? No? Anyway, so see you guys Wednesday. Have an enjoyable week.